Okay, I'd like to revisit this example that we just looked at. Okay, so if you remember, we had this set S. Okay, we put it into echelon form, reducer echelon form. Okay, and the pivot positions told us which of the columns of A are the important columns. Okay, call them the pivot columns of A. 1, 3, and 4. Okay. The other columns, columns 2 and 5, were sort of the unimportant columns. Okay. And we stated that each non-pivot column can be written as a linear combination of the pivot columns. Okay. So the reduced row echelon form tells us a lot of information. And it actually tells us how to do this, how to write the non-pivot columns as combinations of the pivot columns. Okay? And in doing so, it actually gives us a factorization of A. Okay, so let's look at this. So here's what I'm going to do. I'm going to form the matrix of the pivot columns of A, and I'm going to call it C. Okay. So the pivot columns, if you remember, are column 1, 3, and 4. So I'm going to form a matrix with them, just them. Okay, and I'm going to maintain the order that they were in originally in A. That's important. I'm also going to form the matrix R. Okay, the matrix R is the reduced row echelon form of A with any 0 rows deleted. Okay, so this is our reduced row echelon form. We have one 0 row. Okay, a 0 row is a row with all zeros. We have one 0 row, so I'm just going to delete that, remove it from the matrix. So this is going to be my R, a row with, a matrix with one less row. Okay, so I claim I have a factorization here. So let's consider the product CR. Okay, this is C, this is R. Let's multiply them and see what we get. Okay, so as I've emphasized before, when you think of matrix multiplication, you should think about it as a bunch of linear combinations. Okay, and we can think of CR like that. Okay, so the first column of CR is just going to be C times the first column of R. Okay, and the second column of CR, the product, is going to be C, this whole matrix, times the second column of R, and so on. And that's how we'll get our 5 columns. Okay, so now we're going to, for each of these columns, we need to compute a matrix C times a vector here. Okay, and if you remember, I said that computing A times X is just taking linear combinations of A with weights from X. So this is the same thing here, where we have a C instead of an A, and our X is going to be this column here. Okay, so how to think about this? Okay, so C is this matrix here. Okay, you can think of it as a menu. Okay, and what's on the menu is 3 columns. That's what C has to offer. Okay, and you can think of X here as an order. Okay, so the order is saying I want one copy of column 1. Okay, and so one copy of column 1 will be the product of C times this vector. Okay, so C times this vector. Okay, what does this vector want? It wants 2 copies of column 1. Okay, so let me scroll down here. Yeah, so the first column, okay, there's an order of 1 copy of column 1 put in, so this is the result. The second order was 2 copies of column 2, sorry, 2 copies of column 1, sorry. So we're going to multiply 2 times column 1. The third order is 1 copy of column 2, okay, and 0 of the rest. The fourth order is 1 copy of column 3, so just 1 column 3 here. And the final order is the slightly more complicated one. It's saying I want no copies of column 1, and I want 1 copy of column 2 and 1 copy of column 3. In other words, a linear combination of column 2 and column 3 with weights 1 and 1. Okay, so I'm just going to add those 2 columns. Okay, so what happens when you evaluate all this? Okay, you get this matrix. Okay, and what is this matrix? That's just A. Okay, so we found a way to recover A by multiplying 2 matrices together. So in other words, this is A equals CR. A is this is a factorization of A. Right? That's what it means to factor, to break something up into a product of 2 smaller things. Okay. So I'll emphasize it again that the reduced row echelon form of a matrix encodes a lot of information. Okay, so the pivot positions tell you which columns of the matrix are the important columns that form a basis of the column space. So these columns here. And the other columns here, they encode how to write the non-pivot columns, so columns 2 and 5, as linear combinations of the pivot columns, the basis columns. So there's a lot of good information in there. So let's revisit this question about linear combinations we had. Okay, so recall we had this question about linear combinations. Okay, so let's say we have V1 through VQ and some B all inside Rm. Okay, so the question was, how do you determine if B is a linear combination of the V's? Okay, in other words, do weights C1 through CQ exist such that this equation is satisfied? Right? This equation exactly says that B is a linear combination of the V's here. Okay, so now we want to remember what we said about the product AX. Okay, so if A is thought of as its columns, V1 through VQ, okay, and we multiply it by some vector X, okay, which has entries, X1 through XQ, then it looks like this, right? Okay. In other words, a linear combination of the V's with weights given to the X's, or coming from the X's. Okay, so this is an expression for the linear combination of the V's. Can be expressed as a matrix multiplication. Okay, so if we're interested in solving for this expression, we notice that this is exactly the same as this, right? Here we're using x's, here we're using c's. They're both scalars that are unknown, okay? If we want to solve for this, it's the same as ax equals b. Those are the same equations. Okay, so this means that answering our question up here is equivalent to solving the matrix equation ax equals b for some unknown x. Okay. So we've translated our linear combination problem into a matrix equation. Okay. And what can we do with matrices? We can put them in echelon form, and that reveals information. Okay. So this is the setup. We have A, an m by q matrix. We have X, a q by 1 matrix. And we have B, an m by 1 matrix. Okay, so in this scenario, we suppose that A and B are fixed and known, and we're trying to solve for the unknown X, if it exists at all. Okay, so here's the procedure. Okay, so we want to form what's called the augmented matrix, A, B. Okay, what that is we just write the columns of A, and then we write B as an additional column. Okay, so this is going to be what? An m by q plus 1 matrix. Okay, so what do? We put that matrix, the augmented matrix, into reduced or echelon form. Okay, and now there are 3 possibilities for how many solutions we have. Okay, so the first possibility is that there's no solutions. Okay, and that occurs if there's a pivot in the rightmost column. Okay, so the sort of column that used to be B. If that has a pivot in it, that means there are no solutions to ax equals b. And in turn, that means that B is not a linear combination of the V's. Okay, so you have to watch out for a row that's all zeros all the way, and then a 1 at the end, or some, a 1 at the end. Okay, so the next possibility is that there's a unique solution to ax equals b. Okay, so that happens if there is no pivot in the rightmost column, okay, and all the first q columns have a pivot. Okay, so here q is equal to 3, and all the first q columns do have a pivot here. Okay, and that means there's a unique solution, and we can easily read off what the unique solution is. Okay, so this is saying that x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3. Okay, so we have exactly one solution, and it's this. Okay, so this means that B is a linear combination of the V's, and we use these weights to satisfy the equation. Okay, and the final possibility is that there are infinitely many solutions. Okay, so what's the condition? There is no pivot in the final column, the rightmost column. Okay, and at least one of the first q columns, okay, has or does not have a pivot in it. So in this case, the second column does not have a pivot in it. Okay, so what that means for the solution is that x2 is a free variable or a parameter. And that means we'll have infinitely many solutions to ax equals b for x. Okay. And of course that means that b is a linear combination of the columns of A, the v's.